Thanks everybody for coming here at 4:30 on a Friday. I was a little disappointed to realize I'm just going to be right before drinking hour, but I appreciate the big crowd I got here tonight. Hopefully I'm going to be informing you and entertaining you just before you go out, so hopefully you have a lot to talk about tonight. My name is Ron Fosner, and I'm a PC gaming engineer at Intel, and one of my jobs is making PC games run better. And one of the things that we at Intel have seen is that there's a lot of confusion as to how to take advantage of multi-core systems. And that's what I'm going to be talking about today. I'm going to talk about a task-based architecture that lets you scale nicely towards any number of cores that are on a system. So the problem that I want to address is multi-cores are getting more and more ubiquitous. You can't really buy anything like a single core PC today. At the very least, you're going to get a dual core. The trend is just going to get more towards more and more cores. And you really have to know how to take advantage of it. You can't get by just throwing a couple things on threads and say that you're multi-threading. How many people think they have a good understanding of threads and threading? So, not too bad. Okay, good. Have you guys attended the Don't Dread Threads talk? So, do you like that? Okay, this is going to be sort of a continuation on this one. It's going to be the next level to it. How many people think they have a good understanding of the difference between a task and a thread? So, some. Okay, let's see if you know. How many people out there have got a current game engine where you threaded it by throwing the rendering on one thread and a couple other things on another thread, and you think that's threading? Okay, you were the guys that I'm going to be focusing on tonight. How many of you work to keep your game engine as busy as possible in terms of keeping the GPU busy? So, not too many, really. I'm surprised. How many of you are programmers? Okay, all right. So, how many of you have tried to keep the CPU cores as busy as possible? Oh, good. Okay, cool. This is going to be fun then. So this is a slide I stole from our marketing people. And this is our Gulftown system that we've announced this week. It's a nice, sweet system that I don't yet have on my desktop, and I'm jealous. But the important thing to note is this in red. It's got 6 physical cores and 12 threads. This is the current high-end system that we're going to be shipping now. So this is not what really you should be setting your sights on, because if you're setting your sights on this, it's going to be obsolete by next year. What you should be doing is focusing on ways to take advantage of any number of threads that are available on the system so you can scale nicely across it. And that's what I'm going to be focused on, is I'm going to try and describe an architecture to you that allows you to do just that. So my agenda is I'm going to cover a couple of things. My talk is to get you thinking about using tasks as opposed to threads. I really don't want you to think about threads in terms of the architecture that you're working on. I want you to think about threads in terms of just devices to use to get tasks to run. So I'm going to be throwing these terms about, and I want to clarify exactly what I'm talking about. So I want you just try to focus on tasking-based systems and not threading-based systems. So if you're familiar with threads, you may not have taken time to think about the next step, which is actually a task-based system. So I'm going to be talking about 2 different architectures, 2 different samples that I went through. I'm going to be talking about a simple tasking system that I used to implement them both. What I did was I picked 2 problems that I thought were fairly interesting. A simple one that is pretty common to game developers, and something a little bit more visual that would let you visualize some of the threads that are going on. I took a look at some of the architectures out there in terms of the OS and some of the nomenclature, some of the ways that people have done it before, and I tried to pick the simplest architecture that would let me do what I needed to do. So what I'm not going to talk about is the ultimate threading system, the ultimate tasking system. I'm going to try and give you an architecture that you can take home and play with and try and get used to thinking about tasks instead of threads. So the thing that I want you to take away is thinking about tasks and thinking about how you can take your architecture and turn it into a task-based system. So I want to start you down the road of task-based architecture for your next game engine. So there's a couple things I'm not going to talk about, and these are for you to discover. I can't design the best multi-threaded architecture for your game engine. This is something that you're going to have to do. So I'm not going to cover things like thread affinities, the different tasking APIs that are out there. Some of the problems that you're going to run into are like fault sharing, how to apply lockless storage devices, when you should apply mutexes or semaphores or things like that. That's all in the literature. And there's plenty of literature on that. So if you get to the point where you actually have to worry about that, that's a good thing, okay? I want to get you to that point. So programming with tasks allows you to take advantage of the hardware horsepower that's running on the current machine, not something that you're designing for right now, but something that your gamut of users is going to have, including the ones down the road, 5 years from now. Programming threads means that you are responsible for keeping the threads busy. So I want to try and get you off that mindset and onto something like thread pools or some kind of architecture where you have given the responsibility of scheduling things to something other than your code. And at the end, your job should be to make sure that each hardware thread is busy all the time. So basically, the tasking architecture is going to allow you to keep all of the CPU cores busy as much as possible, given your current designs. So what is a task? So a task is usually part of a larger job. So you're going to take some monolithic job that you're going to be doing, like view frustum culling, and break it up into smaller pieces. So it's stateless in the sense that when you run a task, it's usually just a bit of code that's executing. So it's essentially, you can think of it as a function call. And the difference between function calls is that you might apply different parameters to them. So a function is stateless, but the function parameters, which are the context that goes into the function, are how each task is differentiated. So if you look at it that way, it's pretty straightforward as to what a task is. Now, tasks are generally scheduled by a task manager. And this can be, and the sample I'm going to show you is part of the Windows Vista OS, Windows 7 OS. But it can be some piece of code you write. But the object is that it's a black box that you throw these tasks into, and they get executed and retired. And you don't have to do anything about the scheduling. They should be independent from other tasks that are running in the sense that you don't want to set up dependencies between the tasks if you can avoid it. Sometimes you can't avoid that, and I'll discuss that a little bit. But basically, you want to just throw these things into the task manager and let it worry about the scheduling for you. And usually the number of tasks is going to be broken up onto the available hardware threads. So for example, if you're running on a system with 12 hardware threads, you break your job up into 12 tasks, because you can't have any more tasks running than there are hardware threads. There's also some technical details that you might run into. So if you're churning a lot of data over the L2 cache, for example, you don't want to break your job up into many tasks in that sense, because you're going to do something called fault sharing. The other side of the equation is you don't want to make your task too long, because the OS is going to swap it out after a while, and that's usually about, given the operating system and the settings of the machine, something like 30 milliseconds. So you want to schedule them small enough so that they run, but large enough so they aren't going to pollute the L2 cache. And I'm going to harp on this repeatedly, but the only way you're going to find out stuff like that is to take measurements yourself. I want to get you set up, and I want to get you thinking about this so you can run into these problems down the road. Because once you run into these kind of problems, that means you're using all the CPUs. You might not be using them efficiently, but at least I got you to the point where you can deal with the problems later on. And that's the big step I want to get to. So this is more of an introductory class in how to go from threading to tasking and the advantages that you're going to get from there. So this is an example of how OS threads work right now. So right now, if you're doing your own thread scheduling, you've got some work that you got to do, and you've got some threads that can run, so you're going to schedule them. So you manually schedule them, they run on the threads. Eventually, they get done, and they get retired. All right? Now, you have to do all that work if you're doing threading yourself. So that's a bad thing, because that means you have to continually check the state of things. It introduces a lot of overhead that you don't need to do. So there's a different way of doing it, and I'm going to talk about thread pools. Now, a thread pool and a work queue work together to basically keep the CPU threads busy. So the way it works is you throw jobs into the work queue, and the operating system is responsible for taking them out of the work queue and assigning them to threads in the thread pool. A little too fast there. There's some animation playing, you just can't see it. So basically what's happening is, as tasks get done in the thread pool, they get ejected from the thread pool, and the work queue schedules them. They get automatically thrown into there, executed, retired, and all this happens automatically. You don't have to worry about it. So your job as a programmer is just to keep throwing things into the work queue, and the operating system or the task manager is going to take care of making sure that all these things get executed in an efficient manner. All right, so now, work queue, thread pool, how does this all fit together? Thread pools give you some advantages, and in terms they encapsulate the underlying operating system threads. So they give you some platform independence. So the thread pool work queue API is an API that gives you the ability to create a whole bunch of task-based systems and not really worry about the underlying architecture. So you can use, in this case, I'm going to be using the Windows Vista thread pool, but you could create one that works on XP, Xbox, PlayStation. You want to have a similar architecture in place so you can create your work as tasks and distribute it over there and just not worry about it. So the hard part is actually getting to the point where you can break things up into tasks. This is just the magic that's going to happen that makes it really efficient for all this stuff to work. So now, taking a step back, that's how it works internally, but in reality, there's just this opaque thread pool API that you're dealing with. So you don't have to worry about anything that's happening on the inside. You just have to worry about this API that you're programming. So this makes it easy to port the code across, and it also makes it easy to get things scheduled. So the one thing that you're going to have is jobs. So you're going to have different kinds of jobs that you want to be able to submit to the thread pool. And what you're going to need to do is configure them to run the thread pool by breaking them up. So you want to create smaller independent tasks out of the jobs. And then this, I make it sound easy, but it's kind of a little challenging, is to eliminate as much interdependency as possible and then deal with the remainder. And this can be done in a number of ways. You might have to have threads that actually run, or tasks that execute one after the other. There might be dependencies. But the trick to getting this work efficiently is to try and minimize that or deal with it. And I'll go through a couple of examples of how to do that. So what I'm going to talk about is a very simple thread pool API that I created to demonstrate this. And I based this upon the Vista thread pool API. And the reason I did this was because I took a look at the literature on the ways that people have done task-based systems before. And in my attempts to create some of the samples that I'm going to go through, I eventually came across this, and I discovered that this actually had all the features that I needed. It wasn't perfect, and it's not quite ready for production use, but in terms of being able to play around with tasks and task-based systems and seeing if you can get things to work, this worked really well, and I was really surprised at how much mileage I could get out of this API. And the other thing that was interesting was I discovered that Microsoft had been doing a lot of work from Vista and Windows 7 to actually make this kind of stuff much more efficient than it was in previous versions of Windows. So you can actually get some pretty good mileage and pretty good performance just using these straight APIs. Although there are some things that you're going to have to watch for if you're going to try and use this in the game. But in terms of a simple API that you can play with, that you can eventually bring up to production quality, this worked pretty well for me. So what I did was I needed some special capabilities in terms of being able to create tasks. Now, Windows provided the Threadpool API, but I needed to hook this into my task-based system. So what I did was, I'm a C++ programmer, so I put a class around everything, and that usually seems to work. But these are the APIs, the Win32 APIs that I used in my Threadpool API. So basically, you can create a thread pool, you can set the minimum and maximum number of threads, and the really important one is the function try submit thread pool callback. And if you're familiar with threads, this is essentially where you submit your function pointer to get executed on the thread. It's called try submit thread pool callback because eventually you can run out of memory. Although I haven't been unable to do it yet. So you'd have to literally eat up almost all the memory on the PC before you're going to get this to actually block. So it was pretty robust. I threw thousands and thousands of jobs, simultaneous jobs at it, and I couldn't get it to choke, which is more than you really should be having. You should have maybe 1,000 or two for a really complex system. So this is my thread pool wrapper. And this is pretty much it. I mean, there's some functions that go along with it, but they're pretty straightforward. They're usually less than 10 lines. They're just wrappers to construct my kind of tasking-based system to something that Windows is going to use. But the really important function here is the work callback. And this is the callback into the Threadpool API to actually get work done. So at the beginning of the Threadpool class, you see PTP pool. And this is the OS Threadpool handle. And basically everything I'm using is going to be wrapped around this Threadpool handle. So the nice thing about this is it just takes a simple function pointer. It's possible to create other kinds of objects. I just want to create a job that gets fired off, executes, and returns. There's actually some more functionality here. You can create events that get fired off on timers. You can create I/O completion events. You can do registered wait events, which are particularly nice if you've got many items that are waiting together. But this provides a fairly simple API that lets you play with taking your jobs, breaking them up into tasks, and see if you can get in them all to execute. So this is the actual implementation of the work callback, and this is the only part that I needed to do to actually get the functionality that I needed. So I'll go into some of the trials and tribulations I had in coming up with the examples, but it boiled down to I needed essentially three things. I need the ability to execute functions on the threads, which is what the green function does, which is do work. That's simply just my function call into the thread pool. And there's two functions that deal with dependencies. And I wanted the ability to throw work into the thread pool, but have dependencies. So I just wanted to say I have task A and I have task B. Task B is dependent on task A. I want to throw them both into the thread pool and guarantee that A gets done before B. I could have done that scheduling myself, but I wanted to make it the sample as simple as possible. And I could do this using the OS system, so that's what I did. So the red function block if dependencies are pending is actually a block inside there. So we're actually executing on the thread at that point, and we're going to block. So in essence, what's going to happen is the thread pool is going to say, oh, this thread's blocked. It's going to swap it out and swap in some other function that's waiting in the queue of jobs. So this lets me not worry about dependencies as much as I needed to. It lets me have a little bit more independence in terms of scheduling, and it lets me have the freedom of actually creating tasks that are dependent on other tasks or tasks that are subtasks of other things, and basically just throw them into the thread pool and not worry about them. This was actually pretty liberating. I had a lot of fun doing this. After the do work function returns, which means that my task is actually executed, and I've backed out of my function, then the signal dependencies I'm done function is called, and this just goes down the tree of dependencies that the current task that is executing might be dependent upon, and this basically just decrements counter inside each of those tasks. And when that counter is 0, then the corresponding block of dependencies are pending, and that task will not fire. So basically, there's a increment-decrement operator inside each task that records the number of dependencies that it has. So it gave me the ability to actually create tasks, create many subtasks of one larger task and submit them all to the thread pool. And then I could do things like actually have the tasks worry about submitting sub-work, which actually worked out very nicely. So who can tell me what's faster, a mutex or a critical section? Critical section, okay? What's faster, a critical section or a slim reader-writer lock? Who's heard of a slim reader-writer lock? I see 4 hands. Okay, cool. You guys read the same documentation I have. This was kind of interesting to me. When I was researching the Vista thread pool, there was actually a lot of interest in terms of the Microsoft blogs and some of the documentation on speeding up the way that threads and tasks are handled. And one of the things that Microsoft has done is create a couple of new task-based, or I don't want to say semaphore-based, but essentially blocking or unblocking, locking mechanisms that you can use to actually control access to variables or threads that are actually fairly lightweight. They've gone through and they've re-architectured the way that critical sections work, and they've created something called slim reader-writer locks and condition variables. And they've done a lot of work to make these very lightweight in terms of being able to actually access a variable. So if used to critical sections, these work very similar. The nice thing about what they've done is that if there's no contention, there's no context switch. There's only going to be a context switch if it actually has to go into the kernel to actually lock the variable. So if you've got some fairly lightweight stuff that you just want to ensure runs quickly, and you're not going to be, you don't think you're going to be too contentious for actually writing variables, these actually work pretty well. The nice thing about them is they're very simple. They're just structs, so there's really no cleanup. Once you create one of these variables, they're just typically you can either new them or create them on the stack. You initialize them, and that's it. You don't have to really worry about deallocating them unless you nude them. So there's no real OS resources that you have to worry about freeing up. They're very lightweight, and I was quite impressed with how quickly I could get to use these and take advantage of these in terms of getting my tasking system up and running. So this is the interface to my tasking system. And the only reason I have the code that I have here is I wanted to worry about dependencies. So there's 2 kinds of dependencies that I need to deal with. Dependencies that the task is waiting on, and dependencies that the task has remaining that it's waiting on. So the vector list is the tasks that are waiting on this current task. So in other words, these are the ones that have to be informed when this one gets done. The int32 dependencies remaining is just it's a thread safe counter that basically is a number of dependencies that I'm waiting for. So what happens when the current task that I'm running has a dependency, whenever that dependency fires off and gets completed, it's going to go notify me that I can decrement this inside my code, but on its thread. And by the time that my thread goes to execute, ideally this should be 0 if I don't have any dependencies remaining. If I do, then I'm going to block, and I'm eventually going to come back because the thread pool is going to reschedule me, keep checking that variable, and eventually I will unblock and be able to run. So this gives me the ability to schedule tasks that have dependencies and even chain dependencies and make sure they get executed in the right order. So the one thing that I want to cover that makes this possible is the difference between a hardware thread and a software thread. And a hardware thread is the actual physical thread that's running on the CPU, whereas a software thread is that plus all the context that makes it possible. So there's an instruction pointer a stack pointer, all the stuff that you need to actually run on a hardware thread is the software threads. And you can actually have a lot more software threads ready to run than hardware threads. And this is the ability that thread pool gives you behind the scenes. So you can actually schedule many threads to execute, but only the hardware threads that are available are going to actually run those software threads. So let's review what we're trying to do here. So the goal is to keep all of the cores busy. The ultimate goal is to create some sort of an architecture that uses tasks to distribute the task across all of the cores in the current hardware. So you might be able to take advantage of some low-hanging fruit in your current architecture. There's some immediate benefits that you might get from either using OpenMP or something like Intel's threading building blocks. Now, these will allow you to distribute tasks on things like for loops and distribute them across multiple cores with very little effort on your part. I've seen some games increase their performance by 30% just by going through a lot of the for loops that they have and using the OpenMP or TBB constructs to do this. So essentially these are parallel for, pragmas, things like that. And these can actually give you a huge performance benefit from very little effort on your part. So if you don't want to jump right in and create a tasking-based architecture, but you do want to get some mileage out of your current architecture, you can do something like that. So another example of transitioning over to a task-based system is knowing when you need to have things exact and when they can be close enough. So I give 2 examples here. The physics of slow-moving objects and a particle system. So for example, you might have a physics system where you have a whole bunch of stuff going on. For the slow-moving objects, you might consider breaking them off. If they're moving fairly slowly and they're not close to anything, you may not need to update them every frame. So you might be able to break that off and just chop that list of slow-moving objects into 2 and just update either half on every other frame, something like that. For a particle system, that might be something that you update perhaps every 3rd or 4th frame, or perhaps just have the particle system distributed across multiple cores. So you might attempt to distribute, if you have 5 cores, a 5th of the particle system across each one. If you wanted to be a little bit more fine-grained, you could essentially distribute it across 10 cores. And in that instance, you could use some other metric to see if you're, for example, maintaining frame rate. So you keep updating your particle system, and if your frame rate starts to drop, you just start kicking out tasks of particles that haven't been updated yet and schedule them for next time. So in other words, you can distribute your work not only across cores, but across frames. So it's being creative like that and knowing when you can have a little bit of fudge in there that lets you keep the CPUs as busy as possible. So it's a little bit of creativity. You can, I want to try and encourage you to keep all the CPUs busy and also try and plan for non-obsolescence of your game. So for example, you might want to have the ability of running a game on the current hardware now, but say your game is really good and 4 years from now your users go re-download it and try to run it on their 5-year hardware that's got 32 cores and got a 4x NVIDIA card in it and is running at 1,000 frames a second. You want the ability of your architecture to be able to scale up from that. So if you scale things to take advantage of the current CPU hardware in terms of future as well as current, you can actually create a much richer user experience. How many of you have played Wing Commander? Okay. How many of you played Wing Commander recently? Okay. Okay. Wing Commander just ran full bore. There was no timer in the game, and I tried it a couple years ago because I thought it was a fun game. And I got to the loading screen, I started my mission, and then I was dead. So what happened was my 30 or 40 minute mission ran so quickly I couldn't see anything on the screen, and I was just dead from the enemy ships before I could even get a screen update. So that's an example of a bad user experience for when you move to new hardware. And I want to try and set you up so you're going to avoid things like that. because I really had fun playing that game, and I'm sure that your users would like to play your game down the road and still have a much better user experience. So if they can play it on a dual-core system and have a great experience, they can play it on a 32-core system 5 years from now and have a fantastic experience. That's what we're going to go for. And you can do that with a task-based architecture. So now I'm going to move on to something that's really exciting, sorting. So I was looking for interesting visual tasks that I could do, and I'm using tasks in a bad manner, visual jobs that I could do that would translate over to tasks. So I have two samples. And I picked a more mundane one because I thought, well, I'll talk about the maze generation one in a little bit, but I wanted to do something that was a little bit more mundane, a little bit more straightforward, and something that everybody has to do but doesn't think about, and that's sorting. And so I gave myself the job of figuring out how to do sorting on a multi-threaded way, and it turns out that it's really simple. So what I'm going to do is talk about merge sort, which is just a very simple way of distributing a sorting job across multiple cores. And it works because the way that merge sort works is amenable to distributing across multiple cores. And you'll see this theme repeated throughout all the examples. But basically, you need the ability of having tasks that can break up into subtasks that are independent of each other. And merge sort just happens to be an ideal situation, which was quite a surprise to me. So the way merge sort works is you have a list of numbers, and you break it in half. And you break it in half again. And you keep going until you just have one number. Okay? And then you reverse that. But it's called merge sort because you sort as you merge. And you just keep repeating until the list is merged and it's sorted. Now, if you want to make it parallel, it turns out that you need a couple of requirements. So note that each time you split the lists, they're independent of each other. So each time I split, I create these independent lists. Now I'm doing my merge sort in place, so I'm not copying these numbers. I'm just taking pointers to the locations. So these numbers are still in memory. And the nice thing is, I can sort them in any order, or I can sort them simultaneously. So as long as I'm on one side of those dotted lines, I can do anything I want with that list of numbers. So I can sort them in order, or I can throw them on different cores, have them sorted. The only real trick is when I start to merge them, then I start to go from a distributed system down to eventually one thread that's going to be merging the final two lists. But in terms of efficiency, this is really something that's pretty simple to implement. I took a merge sort algorithm that was single-threaded, and I converted it to multi-threaded in about 20 minutes, and it worked fine. It was just dead simple to do. And I was really impressed with something that I thought would be a little bit more challenging. It turned out to be pretty simple. And there's a lot of situations that you can run into that you're going to have some situation where you think you're going to have to do it in a serial manner, but you can actually do it in a distributed manner across multiple cores, and it works pretty efficiently. So the second example that I picked was I wanted to pick something that was a little bit more visual and something that was a little bit more open-ended and unpredictable. And I picked a maze solution algorithm, mostly because I thought it would be really pretty. But the interesting thing is that this actually turned out to be a pretty complex problem, because you're starting off from one known location, and basically there's the algorithm that I use is recursive backtracking. So basically it just goes down a hallway until it discovers a branch point. And then for the single-threaded solution, it saves a branch point, picks the direction that it didn't go in to save, goes off in one direction, and just keeps doing that. And eventually, when it reaches a dead end, it goes back to the last branch point, chooses the direction that it didn't take, and keeps going. Eventually, it reaches the end. It's a pretty simple algorithm. It's really easy to visualize, and it turned out to be pretty challenging. So the algorithm that I picked basically So if you go down to the bottom location where the orange can either go left or the right, this is an example of a branch point. So the way the algorithm works is the mouse I call it a mouse, it's kind of natural. It chugs along till it reaches a branch point, and then it saves the branch point, saves the location that it did not go in, and goes off in the direction that it chose. It can be arbitrary. My mouse always goes to the left. When it reaches a dead end, it marks that part of the maze as a dead end, backs up to the last branch point, and keeps going. And it's pretty simple. So just to give you a flavor of what it looks like, we get the exciting live demo. Okay. Pretty exciting. Let's see. I might go a little bit more. I think I can shut it up. And let it get to a branch point. I keep missing them. I missed. Okay. That's going to be fun to drive. Let's see. So, right here, and at the other locations, I'm actually pushing a branch point onto a stack. And what happens is when the mouse actually reaches a dead end, it just pops that branch location off the stack. So actually it backtracks, colors it in gray, and then backtracks and pops it up off the stack and continues on in the direction that it kept going on. Speed it up a little more. It's a pretty straightforward algorithm. It's kind of fun to watch. Yay. I purposely picked the two endpoints that are furthest away just to torture the algorithm. All right. So let's bring this back. Skip ahead. Okay. So now, the way the single-threaded algorithm works is the mouse keeps going down till it finds a branch point, and the single-threaded solution pushes the branch point on a stack. And for the single-threaded solution, it's pretty simple. When it reaches a dead end, it just goes back to the top of the stack and pops it off. I had a lot of fun trying to make this multi-threaded. It was a lot more challenging than I thought, and part of the problem was essentially that I already knew what the solution was. The multi-threaded solution required me to rethink the way I was doing it. I ran into something that psychologists or psychiatrists call cognitive dissonance. Since I already knew what the answer was, I tried to re-implement that answer. And the problem was that my single-threaded solution prevented me from taking advantage of a lot of the multi-threadedness that I was looking for. I tend to be a pretty anal programmer, and I tend to write code that doesn't create a lot of temporary variables and things like that. And that actually hindered me when I was trying to do this because I was trying to be really efficient and not create temporary variables, which hurt me when I was actually spawning off multi-threaded solutions because I needed copies of the data. I was trying to maintain a minimum data set because that's what I've always taught. You don't want to create multiple copies of your data because that's going to cause you problems. But what I ran into was situations where I was purposely shooting myself in the foot because I was trying to be efficient, and I just had to take a step back repeatedly. I did about 4 iterations of this to try and get back to the situation where I was actually practicing what I'm trying to preach up here, and that was actually kind of fun. Let's go to the multi-threaded version. If I can find my mouse pointer. There it is. I have a countdown on it, so I can tell where it is. So it's the same maze. And as different mice launch off, they're different colors, although they cycle, so sometimes it seems to be that the same mouse is using this, or 2 different mice using the same color. So I'm going to speed it up a little. So for this particular maze generation algorithm that I'm trying to solve, there's not a lot of branchiness into it. And in just looking at it, it doesn't look like I'm getting a lot of benefit out of multi-threadedness. You might notice the difference between this one and the last one is that on the single-threaded solution, I had 1 mouse, and so there's always a trail back to the origin point. In this case, it only goes back to where the other mice spawn it. So what's happening is that we're just creating new mice as the old ones die. So same solution. Now the interesting thing is, if I bring up both of them and run them simultaneously, you be quiet. And I can shrink it. Oop, you want to do that? That's good enough. So I have a single-threaded solution and a multi-threaded solution. So I'm just going to fire them both off. I'm going to let them run. I can make this a little smaller. Now, even though it doesn't seem like I got a lot of benefit out of a multi-threaded solution, just take a look and see what the difference is. So on the upper left is the single-threaded solution. The one on the lower right is the multi-threaded solution. And initially they seem to be running fairly neck and neck. But I'm going to speed up them both a little bit. Yeah, not that much. There we go. So, look at this guy poking along. He's got 26% of the maze done. This guy's got 100%. He used 10 mice. So even though I really didn't see a lot of benefit from it. Initially, I actually got quite a bang for my buck in terms of the multi-threaded algorithm. So it was a little bit of a surprise to me, even though I picked a fairly non-branchy problem. So the interesting thing is, if I bring up something that's a little bit more branchy, and this is just a different maze algorithm. I just maximized it on my screen. That doesn't do me any good. The interesting thing that you see is that depending on the algorithms I have and the way that I'm trying to solve the maze, I can actually get a pretty substantial increase. Sure. I can even try to make them the same size. This is hard to do.
Are you running 7?
This is Vista. Yeah, that's close enough. All right. So this one actually has a lot of branches, but I have a right-handed mouse, and it keeps trying to go over to the right-hand side. So if I go over to the other mouse, the multi-threaded one, where is he? There he is. You'll see a little bit different behavior. So in this instance, there was more opportunity for it to actually branch off, and I got to my solution a lot faster. So it was interesting that the initial problem that I was trying to solve, where I was really trying to give the mouse a hard time and trying to create a really long, narrow path for it, was still pretty efficient. In this instance, I've got a little bit more realistic problem where I have a little bit more branchiness in the solution. And you can see that I got a huge increase. So this one, although it did not take 42 million seconds, I implemented the pause key after I did the timing, so it doesn't work. This guy's still running. So I can run him full speed, but I'll do that later if you're interested. It's a substantial increase in performance when I actually spread it across multiple threads. I got some pretty nice performance numbers. All right, going back. So when I went about implementing my multi-threaded solution, I ran into multiple problems, and most of them were all my fault. I tried to optimize early, and that was a mistake. The one thing that I had to do was actually create copies of variables and pass them along as context for the mice, because I was trying to reuse things and try to be efficient in terms of memory usage, when really that was just hindering me. I needed to code a little bit more defensively. So the one thing that I learned was that if I need to make a copy of a variable, don't be cute, just copy it and give it to the mouse to run. Don't try and be overly conservative if you're looking to get performance increases. The knowledge of the single-threaded solution kept me from creating an efficient multi-core solution, because I kept grabbing onto the vector of branch points and trying to do something with it, because my single-threaded solution would shove these points down on a list, and I kept them around. I was trying to reuse them. So every time a mouse would run across a branch point, it would push it down the list, and I had to schedule something to come back and try and pop these things off. So I was thinking about the best way of doing this, and then I realized that, well, the branch point doesn't contain any history information about where the mouse was, so there's really no way it can know what the origin point was unless I pass the origin along with the branch point. I'm thinking to myself, well, geez, that doesn't work. I'm going to be creating a whole crap load of data that I don't really need. So I have to keep going back and trying to figure out a way of simplifying this. And finally, I had an epiphany, and that is I just did away with the list altogether. I didn't need a stack of branch points. The only thing I needed was the knowledge that when a mouse ran into a branch point, that was the instant that I needed to actually create another mouse that was going in the opposite direction, because I had all the information I needed at that instant. So when I realized that, and I made the mice self-replicating, so one mouse would spawn off another mouse and throw it in the thread pool, I got rid of a lot of the internal structure that I had from my single-threaded solution, and I simplified my algorithms by quite a bit. So what happens is when a mouse reaches a branch point, it just creates another mouse with all of its original context information, including its origin, and just sends it in the other direction. Okay? And that worked out beautifully. I mean, I got to take code out. My solution was a lot more efficient, and it worked really nicely, and I was really surprised. And the problem that I had was I was trying to be efficient in terms of not saving a lot of memory. I was also hindered by the fact that I had this preconceived notion from my single-threaded solution how to solve the multi-threaded solution. So I really had to go back and look at the definition of a task, and a task is supposed to be stateless and independent, and my prior knowledge of how to create a solution really hindered me. So I really had to go back and take a look at the definition of a task-based system and try and recreate that. And when I did that, a lot of the problems I was having melted away because I basically eliminated a lot of the problems I was having. So in terms of applying this to game architecture, what I want you to do is think about some of the jobs that you have and think about how you can break them up and try and create simplified versions of them that are independent. So I discovered that sorting was actually pretty easy. I was actually able to simplify some single-threaded code and make it multi-threaded, and I actually opened up a lot more opportunities for in the maze solution code by having the opportunity to actually have multiple solutions now. I actually get to explore things like that, which is something that I haven't taken advantage of yet, but simply because I have a multi-threaded solution, I can just send off as many mice as I want, and they can all report back to me rather than having to recursively iterate through the entire maze with one mouse. The challenge that I had was actually just realizing that if I could keep things independent and simple, it would actually simplify my task. And that's a big learning curve, and it's something I'm trying to get across today in terms of some of the examples that I did. For example, one of the choices that I made early on was making the mice robust. And this is an example of how to make your code multi-core friendly while not being quite exact. And by that I mean the only real static data I had was the array of cells. And as a mouse would move into the array of cells, it would actually put a value there, which I just happen to call a mouse dropping. But the mouse dropping was an indication of the fact that a mouse was there. So when I spawn off a new mouse and give it a location and a direction, that just gets stored. So what's happened is I could actually have a mouse pointing in one direction, ready to go, and another mouse on another thread could rip by it. All right? Now, I can't know because the mouse that I've got ready to go is suspended in the thread queue. It's not going to get fired off yet. But the very first thing it does when it gets executed is it takes a look at the cell that it's in and sees if the cell is unvisited. If the cell has already been visited, and it says, oh, well, I'm too late, and it just backs out. So in this case, the code is robust in the sense that I don't really need to know exactly the state that the cell array is in, because I always check it right when I'm executing. So I can schedule work that potentially may be wasted work, but I don't need to do things like lock the array and things like that. So the code is robust in the terms that I'm not going to be wasting a lot of effort if my mouse are contending for the same array location. I just need to have them give them the ability of reading the value there. And it doesn't have to be perfect. It just has to be good enough so that they're not going to screw each other up. So I really don't care if two mice decide that the same path is a dead end, or they're going to rewrite the solution to it. The only thing that I have to prevent is them trying to go down a path that another mouse has gone. So if they take a first step and then discover that another mouse has already been there, that's fine. They just back out and just kill themselves. So that makes the code pretty robust in the sense that I don't have to know the exact state of things that are going on, and the code is adaptable. So this actually worked out really nice. This is the one thing I did right, was I planned for the ability of mice overstepping themselves and discovering that they've already been assigned a location that another mouse has already been to. So trying to design a system that works across multiple cores by implementing a task-based system is going to get you a number of benefits. It'll work on any number of threads, so you can scale up or down depending on the current hardware that the user is working on. The thread pool implementation gives you platform independence. So once you've taken the step of actually implementing some stuff as tasks, you can actually implement it on top of a thread pool, and then take that architecture and port it across to multiple architectures. So it should work on netbooks, should work on high-end CPUs, it can work on game consoles. So you should be able to improve the user experience across a wide range of platforms by taking advantage of this architecture. One thing that we looked at that I didn't have a chance to investigate for this conference, but I'm looking for talking about next year, is DX11 deferred context. And this looks like a possibility that might be really good. So what you want to do is give each thread a DX context, and then each task can render to that DX context. And the way that works with the Vista thread pool, you can schedule a whole bunch of tasks to run and then just block on the main thread. And then when all the subtasks are done, you have all these deferred contexts that have been rendered to, you can actually execute them on the main thread. So you're actually doing your present call on the main thread, but you're doing some other DX work on subthreads. I don't know enough about that to give you some definite answers on how to do it, but some of the preliminary work we've done indicates that that works fairly well. Hopefully next year at this conference we'll be able to talk a little bit more about how to do that and some of the best architectures for that. But it is possible to do something with a thread pool architecture to implement that. So the takeaway is start small and build up. Take a look at some of the small architectures that you have. If you can take some small subsystems and start breaking them apart, putting them on a task-based system. And you don't need to switch entirely to a task-based system. You can start off small, create a thread pool, take a small subsystem, break it apart, distribute it across a task architecture, and just get the feel for it. It's actually pretty simple to do once you get the architecture in place, and it seems to be fairly efficient. I want you to just get to the point where you're actually running into problems where you have context switch sensitivities, you're running into L2 cache contention, things like that, because that's the situation that you want to be in, where you're running your CPUs at 100%, but you're having a little problem with getting things to work efficiently. Because once you reach that point, then you can actually start doing optimizations for it. But the hard part is actually taking everything in your architecture, breaking it into small pieces, distributing it across the thread pool, and getting it all to run. So I want you all to go home, figure out how to do that, and then come back next year and tell me what the problems are. And most important is actually measure your code. There's many tools out there that will help you in determining if your threads are actually working really well. So I want you to either instrument it yourself, take a look at some of the tools that are out there, but don't assume that you know what's going on until you actually take a look at that. There's a lot of threading information at intel.com. There's a really cool tool called Graphics Performance Analyzer that Intel is demoing in the booth, which does exactly this kind of task-based system. You can use that to instrument your tasks, even give them names, and watch them execute across multiple software threads. So it's a really nice task. It's not a hardware task, or it's not a hardware threading-based tool. It's a software tasking-based tool. It works really well for figuring out exactly what's going on. I'm going to be publishing this article in MSDN Magazine, so the slides are probably available for me if you email me. I'm going to be trying to be determining how we can make these public. It'll probably be after the magazine ships. But if you have any questions, feel free to contact me. And please fill out the evaluation forms. I want to be able to tune this talk to the problems that you guys are suffering from. So if you have questions, issues, or you just want help in threading, email me, fill out the evaluation forms, tell me what you liked and disliked about the talk, and thanks very much.